and it could crack at the bottom, and the crack would propagate upward, and this type of crack is called bottom-up cracking. Well, if the stress at the top is excessive, cracking may start at the top, and we may have top-down cracking. Okay. However, when you do the analysis, you find that we really don't have tensile stress at the top if you analyze it in the traditional manner. If you put a load at the top, you only have compressive stress at the top. You don't have tensile stress at the top. But in real life, we see a lot of top-down cracking. And why is that? Well, quite a few researchers have studied this problem, and they found out that, well, when a wheel goes over the pavement, there's tire pavement interaction. There's friction in the tire, and it causes some horizontal stress, which could cause cracking. And so, okay, but those stresses are limited to the very top layer. It does not go down, and so, but it's caused by tensile stresses at the top. So can we predict this type of cracking by comparing the tensile strength of the material? An asphalt mixture if we put an asphalt mixture with high tensile strength, is it going to solve this problem? Well, my colleague, Dr. Roque, which Dr. Bunchai had studied under, and actually Dr. Bunchai had contributed to the result that I'm going to present. He studied the problem, and he looked at pavements with top-down cracking problem and pavement with no top-down cracking problem, and he took course, and he measured the tensile strength of the mixture to see if there's any relationship, and surprisingly, there is no relationship. Okay, this is a plot of tensile strength for two groups of pavement, the groups that's cracked and the groups that's not cracked, and this shows the tensile strength. There's no relationship, okay, between tensile strength and whether or not it may crack. Okay. So that's kind of surprising. And what might be related to its resistance to top-down cracking? Well, what he found is that, well, this property called the dissipated creep strain energy, which I'll explain as to how this is obtained. And it's also related to fracture energy. It's somewhat related to fracture energy. If a mixture has high dissipated creep strain energy or high fracture energy, that mixture has much less tendency to have top-down cracking. How is this determined? Well, if you run an indirect tensile strength test, and if it's instrumented properly so that we can measure the strain, then we can plot stress versus strain. So essentially, you get a stress-strain plot. Okay, and if you get the stress-strain plot, you calculate the area underneath the stress-strain plot all the way to failure. This area here would give us the fracture energy. Okay, so a mixture with a high fracture energy would be less likely to have top-down cracking. Okay, and if you take this and you take out this triangular area represent the elastic energy. So, okay, so basically if you take the initial slope here and you use this slope and draw a line from the failure point down, and this triangular area is the elastic energy, and we subtract the elastic energy from the fracture energy, then we have this DCSE. Okay. So we, according to from his research results, a mixture with a high DCSE would have less like have a low likelihood to have top-down cracking. And the question is, well, how much should that be? He want to find the minimum amount. And what he did was he did some crack propagation tests to make a specimen and measure the number of cycles it takes to propagate the crack for a certain length. And I think Dr. Bunchai did some work in this area and had it result in this very useful result. And what he found is that, well, if he ran this test and if it took a very high number of repetition for the crack to propagate 2 inches, that mixture would have a very low likelihood to have top-down cracking. And that number seems to be about 6,000, the number of repetition. And so if it takes more than 6,000 repetition for the crack to propagate 2 inch, that mixture is resistant to top-down cracking. And how much is that? Okay, how much is the DCSE? According to his calculation, it could be expressed by this equation. Oh, by the way, I told Dr. Bunchai that I'm going to leave my presentation here, and so that he can put it on the website, right? So that you can have access to this with all the information, because I think it would be very difficult for you all to remember all what I cover. So all this information would be made available to you all after this, this lecture. Okay, and so this shows the detail of how the minimum amount of DCSE could be computed from the indirect tensile strength test. Okay, and so Dr. Roque suggests that these 2 criteria, okay, in order not to have high tendency for top-down cracking, the DCSE has to be higher than the minimum required DCSE. And this ratio, this ER, is the ratio of the DCSE divided by the minimum DCSE, and it has to be greater than the minimum DCSE. So this ratio has to be greater than 1. This means that the DCSE has to be this DCSE has to be greater than the minimum DCSE, and the formula for the minimum DCSE was given in the previous slide. And also the DCSE need to meet a minimum, need to have a minimum amount, which is 0.75. Okay, so basically in his recommended method, you would test the mixture, okay, and to make sure that the mixture would have a DCSE that's greater than the minimum DCSE, and also that DCSE has to be at least greater than 0.75. And with this criteria, we can predict whether or not we may have likelihood for top-down cracking. And the results, the predicted result matches very well with the observed result. Okay. Well, so how do we design and asphalt mixtures which would not have all these kind of problems, not to have, you know, top-down cracking, bottom-up cracking, rotting, and so forth? How do we design an asphalt mixture? We usually use a asphalt mixture design method, right? So there's different methods. Okay? I believe that in Thailand, you use the Marshall mixed design method, right? Okay, and there could be other methods where you basically design a mixture, and when you get an optimum mixture, and you hope that that mixture would perform really well. And I want to cover the fundamentals of asphalt mixture design here, and I want to cover briefly these four: the Marshall, the Veeam, SuperPay, and also the GTM method. Okay, well, what is an asphalt mixture design procedure? Basically, we select the aggregate that we want to use. We select an asphalt that we want to use, and sometimes we may want to add some additive to it. Okay. And then we make the mixtures, and we test it at different asphalt content. Okay, testing the asphalt mixture at various proportioning of the ingredients. We put in different binder content, and then we select the optimum mix design, okay, that would give the best performance in service. So basically, that's what we do in a mix design method. Okay. So how do we do that? The mixture usually would be prepared, compacted to close to the field condition. Okay, like in the Marshall test, you compact the specimens, and basically you try to compact it to a condition which is close to the field condition. And then you have the compacted mixture, and then you evaluate the property of the compacted mixture. Properties of the mixture would be determined to determine whether or not it will perform. Okay, so that these properties can be used to determine the acceptability of the mixtures and to select the optimum mix design. So we make specimens, we test them, and we decide which one would most likely perform well, and we pick the one that would work. Right? Okay, and so the method involves compacting the specimens, preparing and compacting the asphalt mixtures in the laboratory to simulate the field condition. Then we characterize the laboratory compacted specimens. Characterize means running tests to measure its properties, and we determine the best one based on the criteria that we have set out from the beginning. Okay, so the fundamentals is quite simple, right? You compact it to field condition, then you evaluate it, but different methods are different, okay? And they're different in the compaction method, so the different design methods generally differ from one another by the following things. They use different equipment and methods to prepare and compact the mixture. Okay, in the Marshall method, you use compaction. In other methods, we use different compaction methods. Then if we use different methods, the properties to be measured are also different. Okay? And the criteria used to select them are also different. Okay, so now that we understand the fundamentals, we want to look at these four mixed design methods to see whether or not there are any merits, or whether or not there might be some problems. Okay. Marshall mixed design method was developed by Bruce Marshall, who used to work at the Mississippi Highway Department. This method was not popular until the Second World War. During the Second World War, there was a need to design asphalt mixture for airport runways fairly quickly. They need to design a mixture within a day's time. And so it was adopted during the Second World War, was a very successful method. So after the Second World War, a lot of the highway department adopt Marshall mixed design method was the most popular mixed design method until in the United States until SuperPave was adopted. Okay, but it's still the most commonly used method in the world. Well, are there any problem with the Marshall mixed design method? Well, how does it compact the specimen? Okay, one of the key things in the mixed design method is that we need to compact the specimen so that the specimen would be very close to the actual material in the field. Okay, does it really simulate the actual field condition? Well, how does it compact the specimen? It's by dropping a hammer from this height, a hammer of this weight, 4.5 kilometer, dropping from a height of 18 inches, which is 457 mm. You know, drop a certain number of blows, and you turn the specimen around. You drop a number of blows, and how many blows? Well, it's supposed to simulate actual conditions. So if you have a lot of traffic, you need to compact more so that it simulates the actual condition. And these are typically used. If you want to simulate heavy traffic condition, you could compact 75 blows on each side. Well, is there any problem with this? Well, found that if you compact too much, if you want to simulate really dense mixture, we may have a problem. As you know, those of you who have experience with Marshall compaction method has found out that if you really want to simulate high compactive effort, we may have a problem. You know, it's the aggregate, that's actually the second one. The aggregate tends to get crushed at high compacted level. Okay, it does, and in the field they don't get crushed. They just get, with a higher number of roller compaction, mixture just compacted more. But if you try to do that in the lab, the aggregate got crushed. And also, if you take a core from the field and compare to the Marshall specimens and look at the orientation of the aggregate, they are not the same. So obviously, the Marshall compacted specimen does not simulate field condition very well. Okay, and so that is one problem. In the Marshall method, we measure these properties. We measure air voids, voids in mineral aggregate, percent voids filled with asphalt. Okay, these are volumetric properties. It measures the proportion of asphalt and air and the solids in the compacted mixture. And we also, in the Marshall method, we also run the Marshall stability test, from which we get the Marshall stability and also the Marshall flow. This is a Marshall test apparatus. Those of you who have run the test, I think you're familiar with this. So you run the test at 60 degrees C, and we plot load versus vertical deformation, and the maximum load before failure is known as the Marshall stability, and Marshall flow is the vertical deformation when we reach the maximum load. That's the Marshall flow. And okay, and what is considered the optimum? The optimum asphalt content is picked when the air content is 4%. Okay. At 4%, that's where the optimum asphalt content is, and at that asphalt content, we look at all the other properties, and they need to meet all the criteria as shown here. Okay. Okay. So basically, and the criteria includes Marshall stability, the flow, and then also these three properties: air voids, voids in field with asphalt, and VMA, that's voids in mineral aggregates. Okay, and now that, so